Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, we'll be discussing some problems associated with the theories that we use to predict the shapes of the molecules and how hybridization can be used to account for the shapes that we're seeing. Let's get started. So, as we've discussed in previous videos, we use Lewis theory to help us think about what the overall structure would look like for a molecule, and then ultimately use that to predict the electron and molecular geometries that we are seeing. However, what we don't get is an exact account for why we're seeing some of the geometries that we see are possible based on the electron configurations or orbital diagrams that we know are associated with certain atoms. And so the Lewis theory does give us a good approximation of some of the bond angles that we might expect, but it normally does not account for the actual angles that we're seeing. And it doesn't actually predict the overall shape that we're seeing for some of these atoms. So there has to be some other explanation that's used in conjunction with this Lewis theory to help us to figure out how the bonding is actually occurring and ultimately how we're generating the shapes that we're observing. And so valence bond theory is used to actually think about how the bonding is occurring and ultimately the shapes that we're seeing. And so Pauling and others applied different principles of quantum mechanics to understand the molecules that we're seeing. They reasoned that the bonds between atoms would occur when the orbitals on those atoms interacted to make a bond. And so again, think about the orbital diagrams that we discussed in depth in chapter 8. And a lot of times what they said that this interaction would depend on how the orbitals are able to align with one another, whether it be directly or in some type of perpendicular manner. Now, the orbitals that we're going to be interacting, that are going to be creating these bonds, are going to ultimately be forming these molecular orbitals, which are going to house the electrons that are involved in the bonding that we're seeing, or perhaps the lone pairs that we're seeing on these central atoms. Now, the molecular orbitals would be more stable than the separate atomic orbitals that we've been dealing with, like the S, the P, the D, and the F, because again, they're now sharing electrons from both of these atoms. This ultimately would lower the potential energy of the molecule and should, in theory, make these more stable. Now, this theory does work very well for some atoms. So if we think about something like sulfur and look at its electron or orbital diagram configuration, we know those valence electrons, those 3s and 3p orbitals, we know there's two places in that p sublevel that can hold more electrons. And so it makes sense that we would predict that this H2S, that you could have two hydrogens that can come in and align and be able to make bonding with those residual atoms. And then these remaining would make lone pairs. But what we're going to see is in some situations that doesn't exactly explain what we're seeing. There has to be something else that's going on. Okay, and so this is predicting that we should see a 90-degree angle. The actual angle is about 92, so not terrible. But what we are going to find out that there are several situations in which the angle that we might predict based on the electron configuration that we observe does not align with what we see. And so the solution to this is this process known as hybridization. So hybridization is a process where we're now taking different atomic orbitals and combining them to create these hybrid orbitals, kind of like a hybrid car, which is, a mixture between a gas and electric car. So it's making this hybrid orbital, which will allow for us to account for more configurations that may exist for how the molecule may be shaped. And so a great example of this is like carbon. When we look at carbon's electron configuration, or more specifically the orbital diagram, we know that it would be 2s2, then 2p2, with those two electrons in the p sublevel split amongst three different orbitals. Well, what that kind of indicates to us is that there may only really be two places that we can add electrons. But in reality, we know that there are situations when we're able to make 4 bonding regions, or maybe 3 or 2. So there has to be something that explains this. And so to adjust for these inconsistencies, it's been postulated that the valence atomic orbitals can actually hybridize, again, making these mixtures of S's and P's and ultimately some D's down the line that will allow us to create these regions where bonding can occur. And so if we look at like an unhybridized C orbital and think about the geometries that it would be predicting, well, again, we have in the valence electrons that P subshell, it looks like we only have placement or a place where we can put 2 additional bonds, right? So if we were bringing carbon and hydrogen together, we may predict that only 2 hydrogens can come in and make a pair. Well, we know that's not the case. We know that CH4 exists. So how is that possible? Well, what happens is, again, we actually have this hybridization where we're going to be mixing the orbitals, these S's and P's, to create these new orbitals where electrons can be distributed, and ultimately will determine the shape of these molecules. Okay. So some things we want to keep in consideration: the valence electrons of the atoms in a molecule reside in the quantum mechanical atomic orbitals. And these orbitals can be those standard S, P, Ds, or F, or we'll see in a lot of situations that we do have this hybridization that can occur where we're mixing different atomic orbitals together to make these new molecular orbitals. And then we know chemical bonds result when these atomic orbitals are able to interact, and there requires a total of 2 electrons in this new molecular orbital in order to make a bond. And then the shape is ultimately going to be determined by these new interacting orbitals. All right, so some atoms do hybridize their orbitals to maximize their bonding capabilities. The more bonds you can have, the more full orbitals you can have, the more stable the molecule will ultimately be. And so there are going to be 5 different hybridization orbitals that exist that you're going to want to be aware of. And I'm going to talk about a little trick that you can use to kind of predict the hybridization of a molecule a little bit later. But the hybrid orbitals that we're going to be dealing with are here for you. So if you want to just take a picture or write those ones down, we're going to go through each of these examples. So the hybrid orbitals can be called SP or sp2, meaning we've brought 1 s orbital and 2 p's together. sp3, which means I have 1 s and 3 p orbitals that have been brought together to make 4 new equivalent orbitals. sp3d, which means I have 1 s, 3 p's, 1 d combined to make 5 equivalent orbitals. Or sp3d2, which means I have an s, 3 p's, 2 d's to make 6 equivalent orbitals. The beauty about it is the number of orbitals that you're combining is ultimately going to be the same as the number of electron regions we're trying to account for. So just keep that in mind as we go through this. That'll be kind of the shortcut. And it's really interesting because some atoms can actually hybridize and make multiple types of these orbitals. Like, for instance, carbon can make sp hybrids, sp2, or even sp3 to account for the many configurations that we see that carbon can take on in terms of the shape. So again, with the hybrid orbitals, the number of standard atomic orbitals that we combine equal the number of hybrid orbitals that are going to form. So if I take a 2s orbital, again, that 2 meaning the energy level. So I take an s orbital and then the p orbitals. Well, if I take 1s, 1p, the name of it would be sp, and we would now have 2 of them. Okay, the number of orbitals that I'm combining makes the total number of these hybrid orbitals that exist. Most atoms can hybridize except for hydrogen, so that will only have that s orbital present. And the number and type of standard atomic orbitals combined determines the overall shape of the molecule that you would have. And the particular kind of hybridization that occurs is the one that yields the lowest overall energy for a molecule. Okay, and so shown for you here is all the hybridization schemes that exist for carbon. So again, unhybridized carbon would have 2s2, 2p2 with those electrons distributed as such. Now, in a situation where we need to create 2 electron regions, like in this CHN example, where we have, again, 2 electron regions, well, what we would need to do if we're accounting for 2 electron regions, we need 2 orbitals to come together to make these equivalent orbitals, and those are going to be my sps. So I've brought an s and one of these p's together. And then what remains are these unhybridized p orbitals. Those unhybridized p's, those 2 electrons that are found there, that's what's going to be creating these secondary bonds, the double and triple bond that we ultimately see here. And that initial bond is going to take place there. Okay, we're going to learn those are called sigma and pi bonds, and we'll get into that in a little bit. In something like CH2O, where I now need 3 regions, again, I'm going to bring 3 orbitals together. So I would bring one of my s's and 2 of my p's So the name of it, these equivalent orbitals would be sp2, and I now can distribute those electrons, 3 of them, into those equivalent hybrid orbitals. And then the last one goes into the unhybridized p. And again, that unhybridized p is going to allow us the ability to make the double bond. Or in a situation like CH4, where I have 4 regions that I got to account for, well, now I'm going to be bringing together an S and all 3 of my P's to create 4 equivalent orbitals that are known as sp3. And I can distribute each of the electrons into there. And that will now create 4 equal regions, 4 equal places where I can now align these hydrogens. Okay. All right, so let's jump into sp3 hybridization. So when you have an atom with 4 electron groups around it, something like tetrahedral geometry, you are going to need this atom to take on this sp3 hybridization in order to account for the geometry that you're going to be seeing. The atom is going to use hybrid orbitals for all the bonds and the lone pairs. So whether that be like the carbon in this example here, or the nitrogen, since there's 4 electron regions around each of these, the hybridization for each of these would be called sp3. Again, count the letters. 1 S plus 3 P's tells me 4. So if I'm accounting for 4 electron regions, I need 4 equivalent orbitals created. So bring an S and 3 of my P's together. And the name of it will be an sp3 hybrid. Okay. Now, these hybrid orbitals, as the name implies, look like an intermediate between our s orbital and our p orbitals. We learned back in chapter 8, s orbitals have that spherical shape, whereas p orbitals are that balloon shape. And so our hybrid orbitals are going to look like an intermediate between that, not quite symmetric balloons. And now if we have 4 of those that have been created, well, those 4 can now align, as you can see here, to make that tetrahedral shape. And so that's where the shape that we're observing is coming from. Okay. And again, you can see this hybridization, the orbital diagram, what's happening. If I'm taking these unhybridized standard atomic orbitals for carbon, and now I mix them up to make these equivalent sp3 orbitals, now those 4 valence electrons can be distributed in those 4 positions, and those are where the bonding will occur. Okay. And you can see this happens with both carbon and nitrogen. And like an example we just saw where we had that tetrahedral shape. Well, in that nitrogen, when we distribute its 5 electrons, you end up with a lone pair and then the 3 regions where bonding will occur. Okay, so again, 4 electron regions, the hybrid orbital would be known as sp3. Okay, and we can practice drawing what the hybridization would look like here. For the Cl, if we're making sp3, again, we would end up with 4 equivalent regions. Then we're able to distribute those 7 electrons through. So we would end up with 3 sets of lone pairs, three sets of lone pairs, and 1 place where that bonding can occur. Similarly with oxygen, when we're hybridizing those orbitals, we end up with that sp3, bringing all my S's, my P's together, distribute the 6. You see, we end up with 2 lone pairs and then 2 places that bonding can occur. So think about like when you have H2O, we have our 2 lone pairs and then 2 places where bonding is occurring. With chlorine, every time we see chlorine bound to something, we always see that 1 lone pair and then 3 bonding regions, or excuse me, we have 1 bonding region and 3 lone pairs. So you can see these are my lone pairs. And here's where that bonding is happening. Okay. All right. And so when we are thinking about how this bonding is occurring, we want to keep a few things in mind. According to the valence bond theory, bonding takes place between atoms when their atomic or hybrid orbitals interact or overlap. And to interact, the orbitals must either be aligned along the axis between the atoms, or, so that means they're coming directly towards one another, or the orbitals must be parallel to each other and perpendicular to the interatomic axis. So there's going to be something that's coming perpendicular to that. This perpendicular piece is normally seen when you're dealing with double or triple bonds that involve those unhybridized p orbitals. All right, and so again, just visually showing you what sp3 hybridization looks like with methane. So again, you have these 4 equivalent hybrid orbitals that are created to allow that interaction with those 4 hydrogen atoms. Similarly with ammonia, sp3. So you have one lone pair and then 3 places where that bonding can occur. Okay. Now, you're going to hear some terminology thrown out a few times on how we classify the bonding that's occurring. When you have bonding that is the result of the interacting atomic orbitals along the axis, basically coming directly towards one another, those are what we call sigma bonds, okay? And they get the symbol of sigma. And when you have that perpendicular attraction that's happening to the axis, those are what we call pi bonds. And this is going to happen with these unhybridized parallel p orbitals. And so in a bond, when you have a single bond represents a sigma bond. A double bond represents a sigma and a pi bond. And a triple bond would represent a sigma and 2 pi bonds. Okay, and those pi bonds being the result of those unhybridized p orbitals that are able to do that. In general, your sigma bonds are going to be stronger than your pi bonds, but the combination of a sigma and a pi bond to create a double or a triple bond will ultimately be the stronger of the two. Okay. And so this is just showing you those perpendicular orbitals that can come to make those double bonds, your pi bonds. Or if they're coming parallel to one another, then that's your sigma bond. Okay. And so with the orbital diagrams for bonding, that overlap that's happening between a hybrid orbital on one atom with the hybrid or non-hybridized orbital on another is the sigma bond. So again, that's that first interaction that may occur. And the overlap that happens between unhybridized bonds or unhybridized p orbitals, those are your pi bonds. Okay, so make that declaration. How many sigma bonds, how many pi bonds do you have in a molecule? Okay, and so in this example here, CH3N2, we would say that we have 1, 2, 3, 4, 5, 6 sigma bonds that are occurring, that direct alignment, that initial contact point within the molecule or atoms that are present here. In formaldehyde, well, now we have that double bond present. And so we would, in this case, have 3 sigma bonds and 1 pi bond. And that pi bond is the result of this unhybridized p orbital that can now align with each other to make that second interaction. Okay. All right, so sp3, that's when we're dealing with 4 electron regions. 1s, 3 p's gives me 4 hybrid orbitals. Now, when we're dealing with 3 electron groups, well, that means I only need 1 s orbital, 2 p's, so that's sp2. And this is where we're going to be able to make that triangular planar shape, okay? And so you can see that shown for you here. So again, 3 electron regions, hybrid orbital be sp2. We could also count the number of sigma and pi bonds shown here. Again, that single bond, each of these single bonds represent sigma bonds. And then one of the bonds in the double bond would be a sigma and one would be a pi. So in this case, we have 4 sigma, 1 pi bond found here. And that pi is from that unhybridized p orbital. Okay, and so again, those hybrid orbitals can combine and they're going to create that triangular shape that we know is existent with 3 electron regions. Okay, and then again, showing you these orbital diagrams. You may need to be able to show this hybridization, but really, as long as you know that the naming of the hybrid orbital, that should be sufficient. But check in with your teacher to see what level of detail they want you to be able to do. You should be able to go from unhybridized atomic orbitals to these hybridized orbitals by simply combining the number of orbitals that you need that account for the electron regions that you're dealing with. 3 electron regions, 3 orbitals come together. So an S and 2 P's makes sp2, and then you have 1 P that's remaining, and that's where a double bond can take place. Okay. So in this case here, if we are dealing with an unhybridized atom that's shown for you here, what kind of bonding would you expect? Well, if we're making sp2, that means that we're going to be bringing 2 P's, 1 S, so we have 3 orbitals in this first example. where all three of those electrons can be distributed, and nothing would go in that unhybridized P. And so in this case, the first example, you would expect 0 pi bonds present. In the second example, where now I have 6 electrons that I'll be distributing, well, I'm bringing 3 of them together to make my sp2. I notice when I distribute my electrons, still distributing kind of similar to Hund's rule, give one first and then make pairs. Well, we would have one place where a sigma bond could take place and one place where a pi bond can take place, okay? All right, and then you can see in this picture here a very nice representation of what that perpendicular bonding would look like with those unhybridized P's. Okay, remember a double bond is one sigma bond, one pi bond combined. Okay, and again, you can see that here where you're taking your nitrogen and your carbon and looking at the hybridization that's occurring in each of these. For carbon, we need 3 electron regions, so we know we're creating sp2 hybrids. The nitrogen, we also need 3, so again, sp2. So you would have this one unhybridized p orbital that exists in both, and that's where that pi bond comes from here. Overall, we would have 4 sigma bonds in total and 1 pi bond. Okay. Now, the addition of these pi bonds to a molecule are going to restrict the ability for a molecule to rotate, okay? If you just have that one singular connecting point through a sigma bond, you would see kind of free rotation that can occur. But if you have a secondary interaction here, well, now that restricts the rotation that can happen around that axis, okay? So just remember, when you have a double bond or specifically a pi bond present, the rotation would be limited in that molecule. And so you can see in this example here to the left, where you only have a sigma bond, well, that molecule around that bond would be able to rotate freely. Whereas on the right, with this double bond present, well, now that's locked in position. And so you would not be able to have that free rotation occur. Okay. And again, same thing here. You can see this free rotation, which could take our chlorine from being on one side to the other side of a molecule. Okay, so free rotation. But if you have that double bond, that rotation is going to be restricted. Now, that restricted rotation does also play into the overall polarity that we might expect for some of these molecules. Since it cannot just rotate freely, you end up with situations where you could potentially have this more electronegative region created here versus if they're on opposite sides of the bond. And so when you have these two groups, these functional groups on the same side of a double bond, that's known as a cis transformation. And when they're on opposite sides, that's known as trans. So if we looked at these two and tried to compare the polarity of these substances, well, we would expect the one on the left might be more polar just because you have that greater electron-rich region created and it's not symmetrical across that double bond. Whereas in the trans situation, the pull that's occurring is happening symmetrically, okay? All right, that was a little sidetrack. Let's get back to our hybrids. So when we're dealing with 2 electron regions, the name of that hybrid orbital is known as sp. Bring one s, one p together. That means that you have 2 p orbitals that still remain unhybridized, which can be used for creating pi bonds or ultimately double and then triple bonds. So in this case here, we would have sigma bond and a sigma bond along with 2 pi bonds created. Okay. And again, you can see how those orbitals would align and then the subsequent perpendicular orbitals that come to make those double and triple bonds. Okay, and again, you can see predicting what the electron distribution would be in these hybrid orbitals. As we're making sp, bring one s, one p together to make these 2 equivalent hybrid sp orbitals. And then you have 2 remaining unhybridized P's, and that's where your pi bonds can occur in the carbon example. Same thing in the nitrogen example, 2 sp orbitals are created, 2 unhybridized P's remain, and so that's where that double bond can occur. And then if you look at the orbital diagram, again, you can see that these two remaining unhybridized P's are where those double bond and triple bond would be created. Okay. All right, so we've dealt with 2 electron regions, that's sp, 3 electron regions, sp2, 4 electron regions, sp3. Well, what happens when we're dealing with 5 electron regions? All right, because now we're out of orbitals. So what happens is, especially in these molecules that are in the 3rd energy level or higher, remember, when you're in that 3rd energy level, well, now you have these unhybridized or unoccupied d orbitals that are also available to you. And so in regards to how we create our hybrid molecule, we're going to be pulling all of our S's, all of our P's, so that gives us 4 equivalent orbitals, but then we're going to bring a D into play to give us the ability to make 5 additional orbitals. This is why when we talk about being in period 3 or lower, a molecule can have more than 10 electrons in that central atom. Well, it's because you have access to these available or empty D orbitals. So the hybrid name for something with 5 electron groups would be sp3d. And again, those unhybridized d orbitals could also be used to make pi bonds or double bonds like you see in this example. Okay. Again, here we're mixing all of my S's, 3 of my P's, 1 of my D's to create these equivalent 5 sp3d orbitals, which allow to make this trigonal bipyramidal shape. All right. And so again, here, as this hybridization, this mixing process is occurring, when we make these hybrid orbitals, it creates 5 equivalent places where I can place these 5 electrons. And so the result, you end up with 5 regions that can now be symmetrically positioned around the central atom. In something like sulfur, like in SF4 example, you would have places where 4 bonds can occur and then those 2 lone pairs. Okay. All right, and SOF4, again, this is where using those unhybridized d orbitals is where we can create those pi bonds and allow us to have more electrons around the central atom. Okay, so in total here we would have 1, 2, 3, 4, 5 sigmas and 1 pi. Remember, a double bond is a sigma and a pi. Okay. And then last but not least, when we're dealing with 6 electron regions, well, now we're bringing an S, 3 of our P's, 2 of our D's to create 6 equivalent hybrid orbitals known as sp3d2. Again, count the letters. The number of letters coincides with the number of electron regions we're accounting for. And again, we'll distribute those electrons, and that's going to allow the positioning or the placement where we can make these bonds occur. And so again, here we're going to be mixing to form these different orbitals. Okay. So with sp3d2, it's something like SF6, where we need 6 regions to account for. Well, we bring an S, we bring 3 P's, we bring 2 D's, and that's going to create 6 equivalent sp3 orbitals where I can distribute all of my electrons. And so now we would expect that in something like SF6, I can have 6 bonded things to this atom. Okay. In the iodine example, we may have 5 bonded areas and a lone pair. Okay. And so this is the piece that you need to know. So take a picture of this. This slide will be really helpful for you. But again, you can predict this hybridization the moment you figure out the electron geometry. If the electron geometry is linear, meaning there's 2 electron groups, the hybridization will always be sp. If there are 3 electron groups, electron geometry is trigonal planar, so we would say sp2. 4 electron groups, name would be tetrahedral. The hybridization would be sp3. Count those letters, 1 S and 3 P's gives me 4. 5 electron groups would be trigonal bipyramidal. And so the hybridization will be sp3d. And 6 electron groups, the name would be octahedral, and the hybridization will be sp3d2. Okay, and these are what are determining the actual shapes that we're observing. Okay. So again, put everything together now that we've talked about in this chapter and last. We're going to start by drawing the Lewis structure if it's not provided for you. use the Vesper theory to predict the electron group geometry and the around the central atom. You can use the table I just showed to predict the hybridization, and you can count the number of sigma and pi bonds if you are asked to. Okay. And so if we put all that information together, we want to now predict the hybridization and the bonding scheme for this molecule. Okay, so if we look here, well, we would say the electron geometry for this is tetrahedral. And that's the same as the molecular geometry. We would say here, the electron geometry and the molecular geometry is trigonal planar. No lone pairs, 3 bonding regions. So immediately from the fact that I see tetrahedral and trigonal planar, I can predict the hybridization. I can say that this should be sp3. I need to account for 4 regions. And here I can say this is sp2 because I'm accounting for 3 regions. In terms of the bonding scheme, we count how many sigma and pi bonds exist. I would have 1, 2, 3, 4, 5, 6 sigma bonds and 1 pi bond. Okay, and that would be putting everything together. Okay, so again, count those electron groups, determine the geometry, and then you can go about figuring out how many sigma and pi bonds are present. Okay. So again, here they're explaining how you can translate from the electron geometry to the hybridization. 4 means sp3, 3 means sp2, and then predict those accordingly. And then we would be able to state where are sigma and pi bonds as shown for you here. Okay. All right, one last problem. We want to predict the hybridization for the atoms that are in H3BO3. And so if we look at our Lewis structure, well, we know that here, this would be for our electron geometry, would be trigonal planar, because there are 3 electron regions, no lone pairs. That would be the same thing as my molecular geometry. For each of the oxygens, I would say the electron geometry is tetrahedral, and the molecular geometry is bent. And so that means I have a total of 4 regions that I'm accounting for and 3 around the boron. So the hybridization for the boron would be sp2. The hybridization around each of the oxygens, I have 4 regions that I'm accounting for. Again, base it off the electron geometry, would be sp3 for each of these. And then in terms of the bonding pattern, well, we would say we have 1, 2, 3, 4, 5, 6 sigma bonds and 0 pi bonds. Okay. So I hope this information helped you tie everything together on how to go about predicting the hybridization of these different molecules. Make sure you guys like, comment, and subscribe, and let me know what other information you would like to see. Come back for more videos. We'll be touching on chapter 11 up next, and I'll see you guys soon. Have a great day. Talk to you later. Bye-bye.